Okay, hello everyone. This is Puya. Today I'm just going to talk about three-phase inverter. It's going to be a short topic because we're not going to go into details. Well, like three-phase inverter is definitely like a very broad topic, but for this course we're going to focus on basically like an introductory part of the three-phase inverter. So like we just like see what three-phase inverter is, and we'll see how we do modulation, sinusoidal modulation for three-phase inverter, and that would be it. So this is basically the schematic of a three-phase inverter. So instead of the switches, I use this basically these symbols. Like you would have switches here, either MOSFETs or IGBTs. You will have here excuse me. So we have two DC voltage sources. Both of them have the same voltage, VD divided by 2. This is the neutral point. And then we have 6 switches in 3 different legs. And each leg would be basically giving the output for one phase. So this would be giving the output for phase A, phase B, and phase C. So as if we have a half bridge for each phase. So this is going to be half bridge for phase A, this is going to be for phase B, and this is going to be for phase C. Again, similar to what we did for a one-phase inverter, in this case we're going to have one upper and one lower switches to be complementary. Means like when this is on, this will be off. When this is off, this will be on. The same thing for switches on the other 2 legs for phase B and phase C. Okay, so and this is basically our load. We have a star connection here, and we'll see how these this circuit would generate a 3-phase voltage for us and a 3-phase current for us. So as I mentioned here, like we have 6 switches and 3 different legs. Because the lower level switches are going to be determined, their status is going to be determined by the status of one like the upper level switches. So we can just like draw a truth table based on these 3 switches. Okay, so because we have 3 switches, we're gonna have 2 to power 3 different states, or 8 states. As you see here, I have a truth table here that basically tells us like what the status of the switches can be. From 0, 0, 0 means like when all these 3 upper switches are off, which means that the lower ones will be on, up to 3 ones where all the upper level switches will be on and the lower switches will be off. So if that's the case, let's see what the voltage of phase A compared to neutral, voltage of phase B compared to neutral, and voltage of phase C compared to neutral would be for each of these states. So in the first one, we have we have upper level switches off. So let's look at the phase A, right? If we look at phase A, it would get connected to the neutral point, so that the voltage that goes across, because like the lower level switches on, the voltage of phase A versus the neutral, it's going to be negative VD over 2, because this is basically how they get connected. Voltage of B and C the same way, because the lower level switches are on, so they get connected to basically this DC source. So, and because of the polarity, the voltage is going to be negative VD over 2. In the next one, I'll just like do maybe 2 or 3 of them. In the next one, we have one upper off. So it means that the lower one would be on. So again, voltage of phase A with respect to this point, it's going to be negative VD over 2. voltage of phase B, because again 2L is on, it's going to be negative VD over 2, and voltage of phase C, in this case because the upper switch is on, it's going to be equal to VD over 2, positive sign, right? And for this one, again, VAN and VCN are going to be negative VD over 2, but VBN, because it gets connected to this source, it's going to be positive VD over 2. And the same thing continues for the other states. When we have all the three upper level switches on, all the three phase voltages with respect to this neutral point, it's going to be positive VD over 2. Okay. Now we're gonna see how we basically fire these switches, like how we trigger them, how we control them. Now again, similar to what I did for the one phase inverter, so first I do the analysis and I draw the waveforms, assuming that we only have one pulse per cycle. So it means that the frequency is 1, right? Assuming that the frequency of the switching is 1, this is what we have. So let's look at how we fire the switch for the first leg, for phase A. In this case, we're gonna have the switch on for half of the cycle, so 180 degrees, or the period over 2, and it's going to be off for the second half. And because that's the case, the lower level switch, it's going to be inverted version of the upper level switch, so it's going to be off for half of the cycle and on for the next half. Now, well, we want to have like a three-phase voltage, right? In three-phase voltages, they have the same magnitude, like a symmetrical three-phase voltage, they have the same magnitude. The only difference is that they have phase shift. How much is that phase shift? Is 120 degrees for each two phase, right? So and because of that, we are gonna fire this switch that belongs to the leg for phase B 120 degrees with 120 degrees phase shift compared to what we did for one upper. So like you see here, the switching happens, like we fire this switch at this point, 2t over 3, which is going to be 120 degrees, right? So it's going to be on again for 180 degrees and off for the rest of the cycle, for the rest of the period, and this would go on. I only draw one period, but it would continue. And again, the lower level switch would be complementary of that, so it would be the inverted version of this. So that's why we have having it on here and then off here, and then it goes on. And voltage of phase C would be 120 degrees phase shifted from phase B, or 240 degrees or negative 120 degrees phase shifted from phase A. So that's what we end up here. So you see that here we have 240